So this is very much the basics, the introduction to impedance spectroscopy, particularly electrochemical impedance spectroscopy, from the maths and theory perspective. And I built this lecture after having had so many conversations with colleagues and students for whom it felt like the first step was missing. So they could talk to you about whether they felt it was a good fit for some particularly elaborate battery model, and you look at that one and you see it in the paper and you say, oh, there's a bump there. But if you ask them where a semicircle comes from with this thing, they couldn't necessarily give you the maths behind that bit. And I think we need to bridge that gap for you to feel confident about interpreting your data. And it's not so bad. It's not, in the next hour and 40 minutes, this will all be yours. So I'm going to talk about all this stuff, so just so you can get a sense of the kind of things that we're going to cover. But the core of it is just starting from the absolute beginning and getting to the middle, rather than spending ages just going off about detailed, distinct battery models. So what are we doing? So impedance spectroscopy is much broader than electrochemistry, and it's applied in lots of circumstances like mechanical systems or audio analysis or light analysis as well. And you are applying a small periodic signal, and you are measuring the response. That's at the very heart of it. So there is a small periodic signal, and in this case, because we're electrochemists, it could be a voltage, and we're going to observe and measure a periodic response. And of course, the vertical axis of this thing, where's this little thing down here? Go away. I don't know. Is one of them is a voltage, one of them is a current. You can stimulate the voltage and measure the current. You can also stimulate the current and measure the voltage if you wish. Why are they small? Okay, and you might have heard the concept of linearity being brought up when discussing impedance spectroscopy. And the reason we talk about linearity is because we need a linear relationship between the inputs and the outputs of this system. However, as all of you will be acutely aware, most electrochemical systems that you interact with are highly non-linear. If you double the voltage applied to a battery, you're very unlikely to see double the current. It might be something in that ballpark, but it's not going to be literally ×2. So, even for a highly non-linear process, if you zoom in far enough, in a small region, it will probably look a bit like a straight line. So if the curvature isn't too severe, then if you zoom in far enough, it looks like a straight line in that region. And so we are going to approximate linearity by having a very small signal. So when I say we're going to apply a very small, perhaps sinusoidal voltage, the reason it's small is because even though your battery is a very non-linear object, if you just apply a very small voltage and you double that very small voltage, you will expect to find double the very small current. Okay, so that's the core thing. If you have a very small signal. However, as you can imagine, and we do that because the analysis is easier, but as you can imagine, if you put in a very small stimulation, then the response is going to be very small as well. And that makes it hard to measure. So there is a trade-off going on here. You want the signal to be as small as possible to make it linear, but you want it to be as big as possible to have a good signal-to-noise ratio in your machine. And that is why you pay lots of money for a very high-quality potentiostat, because it is able to generate and measure with very high precision voltages and currents. Okay? And that means your signal can be smaller, which means your response is more linear, which means your measurement is more accurate. So the core message, and we're going to come back to this later on, is that impedance, which we refer to with Z often, is not the ratio of voltage to current in the time domain. It's not V of t divided by I of t. It is the ratio of voltage to current in the frequency domain. And that's a different way of looking at this problem. I'm going to explain what the difference is. But that's a really important distinction, which I think is the major stone that people trip over on their way into impedance. So when we are exploring impedance, we know that there are a range of sort of classical components, simplified components, which we use to explore and represent these devices. So you've got resistors, which are sometimes a squiggly line and sometimes they're a rectangle, and they're usually referred to with the symbol R, and they've got the unit of ohms, and you know the relationship V equals IR, Ohm's law. You've got capacitors, and they have capacitance. They're often referred to with a capital C. They've got the units of farads, and they have mean that each of these things has many relationships, but they have the key relationship of the voltage is 1 over c times the integral of current, the time integral of the current. Okay? And when you think about current, current is moving charge. So if you integrate current, it's how much charge has been accumulated, which obviously should sound immediately like a capacitor to you. And inductors. So inductors have inductance. This should go away. And it's often represented with an L, and it's got the units of henries, H, and that has the relationship that the voltage is equal to L times the derivative of current. So the change in current, or the acceleration of charge. Okay? And we'll come back to each of those relationships later and build them into a single framework. So here is a simple series circuit with all of those three components in it. R, L, and C, resistance, inductance, capacitance. And if I apply a small sinusoidal voltage to this thing, I would expect to measure a small sinusoidal current coming out of it. And what I'm interested in is the relative amplitudes of those voltages and currents and the relative phase shifts of those voltage and currents. So you notice not only could the waves be different heights, but they can also be in a different temporal order to each other in terms of when the peaks and troughs arrive. One of the key things to remember is that all of the components are idealizations. So even, for example, even the wires. So in a equivalent circuit model, you will see black lines connecting each of the components. And we assume that those black lines don't even have any resistance. The black lines connect to resistors. Okay, so we're assuming the wires have no resistance. That's, of course, not true. And in fact, wires don't only have resistance, wires also have reactance, which is this sort of complex impedance part of it. If you send a high enough frequency signal through a wire, you start to get recirculation currents and all kinds of complicated things happening. So all of the components are idealizations. Even the idealized resistor has got a more simplified behavior compared to an actual resistor that you would buy. Okay, every component's ultimately probably going to have a bit of reactance in some sense because it's attached to some wires as well. So they're all simplifications. And if you pass enough current through a resistor, it will set on fire. And that's not built into V equals IR. So they're all simplifications. And as I mentioned, there's this interesting thing with wires, which people are often not aware of, and it's why transmission cables are designed the way they are. If you just have a big, thick piece of metal, almost all of the current, if you put a high-frequency AC signal through it, ends up going through a very thin skin around the outside of the wire, and not, as you might expect with a DC current, just a mass movement of electrons. And you get these recirculation currents and eddies, and your impedance of your wire goes up and becomes a function of frequency, even though it's just a wire. So things are much more complicated than they can often appear. The way I like to think about impedance is by analogy to some more tangible physical systems. And I'm going to introduce three of them, or compare three different systems to you. So the first one is a spring mass damper system. So imagine a little trolley. It has some mass and it's on some wheels and can move around on a surface. It's attached to a wall with a spring, and it's also attached to a wall with a thing called a damper. You know how springs work. As you move away, the force in the spring linearly increases. As you move towards it, the force in the spring linearly increases, but in the opposite direction. A damper is a device that dissipates energy proportional to the speed at which you're traveling. So the spring cares about where you are as to how much force it's offering. The damper cares about how fast you're moving as to how much force it's bringing. And both of them resist you. Both of them push back in the thing that you're trying to do, push back against the thing that you're trying to do. But the mass wants to continue what you were trying to do. Okay, it's slightly hand-wavy language, but the mass, when you think about this trolley, it's got momentum, and if it's moving in a certain direction, the mass causes it to continue to move in that direction, even as the spring starts to push it back in the opposite direction. So, three parameters fully characterize a system like that. The mass, m, the stiffness of the spring, k, and the damping constant of the damper, c. And you can imagine the damping constant of the damper could be perhaps the viscosity of the air inside a piston, something like that. we have an equation that fully describes that system. The units of every term in a sum must be the same. Okay, it's just a general sort of engineering statement, right? If you've got something equals something, they must have the same units. Okay, so when you have F equals ma, well, you know that the force has units of newtons, so you also know that even though mass has units of kilograms and acceleration has units of meters per second squared, you know that combining those units together must also result in newtons. Force equals force. And also, force equals force plus force plus force plus force. It can be no other way. So, all of the terms in this equation are forces measured in newtons. The first term is ma, okay? Mass times, I'm using those hyphens to mean the second derivative of position, mx double prime, plus c times x prime, so our damping coefficient multiplied by our speed, the first derivative with respect to space, plus k times position, so the spring cares about where you are, so if you move forward, the spring pushes you back in units of newtons, equals some force, which could be a function of time. Okay, so that is a second order heterogeneous ODE, the kind of things that a first year engineering student will bump into and maybe never look at again. But it is actually very much like the impedance systems that we're going to analyze. If you don't like that, how about this? This is a water circuit. Okay, so you've got a pipe and it's got three things in it. It's got a constriction, okay, a narrowing of the pipe. As you narrow a pipe with a constant flow, you might end up causing your water to become sort of turbulent and skin friction and heat up the pipe and dissipate energy out of the system, slow the flow down. It's also got a water wheel. Okay, you can imagine this thing turns as the water passes it. The water cannot pass without turning the wheel. This water wheel has rotational inertia. So once it's slow to start spinning, but once it started spinning, it wasn't want to slow down either. Okay, so it keeps things going in the same direction. And the last component, this little black curve, is imagine a sort of elastic membrane in the pipe, fully crossing the pipe. And this elastic membrane can be stretched, and it has a stiffness, but it wants to relax back to being flat again. So if you push water through this pipe system, this membrane is going to start deforming down again, and then if you take your sort of force off it, it's going to relax back and push everything back to where it was before. Okay, so those are our three components, and that has exactly the same governing equation. Okay, I'm going to call, and so I've got alpha, I've just arbitrarily named my constants alpha, beta, and gamma. One combines with the acceleration. I've called this V, volume of displaced water. Okay, X in my spring mass damper was position of the trolley, and V is sort of like the amount of water that's moved in a particular direction. Okay, you could have also kind of used X in this situation as well, but let's have it as volume of displaced water. So would someone like to tell me, of these three components, which one is described by, or which one does the alpha parameter describe its behavior? So looking at the spring mass damper, the mass of the trolley is the thing that gives it momentum and causes it to keep going in the same direction. In this water system, I've also got a term that's the parameter in front of the second derivative. So it's going to have the same behavior like the mass did in the spring mass damper. Which of those three components is parameters by alpha? Very keen to have a guess from the audience. Got a 1 in 3 chance. That's pretty good.
The narrowing of the pipe.
It's not the narrowing of the pipe, so you've now got a 1 in 2 chance. It's pretty good. It's the wheel. The wheel wants to keep spinning in the same direction it was spinning. The mass of the trolley wants to keep moving in the same. They are both inertias. One's rotational, one's linear. Okay? So alpha is this middle component here as the coefficient in front of the second derivative. Beta, thinking again about the spring mass damper, which had C as the damping constant, which was how energy was dissipated out of the system. It was the damper of the system. Beta is proportional, the parameter in front of the speed of flow of the water. So which of these remaining two components is beta parameterizing? You've got one and two chances. Pretty good. The porous plug is correct. Exactly right. Okay, so beta is the sort of narrowing of the thing, the porous plug. It's how energy is dissipated out of the system. Okay, which means that gamma must be describing something about the elastic membrane. And it is. It's the sort of stiffness of the membrane, just like K was the stiffness of the spring. And this is, of course, exactly the same as an LRC series circuit. These three systems are exactly the same mathematically. They have no difference at all. Okay? So, given what you know about resistors, I'm about to reveal an equation here, obviously. And it's going to be second derivative, first derivative, zeroth derivative equals something. First clue, the right-hand side is going to be V, volts. So it's going to be a bunch of stuff, three things added together equals voltage as a function of time. Okay? You have some sense of what resistors are like, capacitors are like, inductors are like. Could someone tell me which of these three terms, first, second, or last, is going to have the resistor as its parameter? Maybe in the middle here. Yes, correct. And so is it the first, second, or third term? The second term, exactly right. Okay? So the resistor, or the resistance, is how energy is dissipated out of the system. And so it's going to be resistance times some first derivative equals voltage. Well, you know a famous equation, V equals IR. I is the first derivative of displaced charge with respect to time. So if Q is displaced charge, then dQ by dt is current. Okay? So we've just got L and C left. A capacitor is very much like a spring, and I think people have that vision in their head already. A capacitor pushes you back. So this means that the inductor must be the kind of momentum term of this system. The inductance wants to keep going in the same way it was already going. Okay? So the L is going to be in front of the second derivative. So that's like the acceleration of displaced charge. And the C is going to be in front of the displaced charge. However, there's a small difference. So we've got it all right except for this one here, which is not C, it's 1 over C. And so if K in my spring mass damper, if K is stiffness, I could also, if I wanted to, have a different parameter called L, oh no, L's a bad choice, called Z, and Z is also a bad choice, Y, which was 1 over K, if I wanted to. I could have stiffness, or I could have some kind of inverse stiffness, which I could call softness. Okay? And equally with my membrane here, I've used gamma, but if I wanted to, I could have 1 over gamma, and I could call 1 over gamma like how flexible this thing is. So I can either think about how much it resists being flexed or how much it likes being flexed, okay? And by convention, we use C, which happens to be 1 over the parameter in front of this Q term here, okay? Which means that a very high value of C is not a stiff capacitor. It's a very soft capacitor, okay? And that makes sense in terms of the notion of having capacity, because your capacitor, if it has a very high value of C, can accept lots and lots of charge coming into it without pushing back with too much voltage. Okay? So that's what's going on there. So you've got these three systems, and now when we talk about them, I mean, I tend to actually sort of think about this one, because this one is just this one. Like, the water is electrons. That's what's going on, right? Okay, so we've got our system here. Now, you won't have necessarily bumped into it much having Q used. You will be more used to having currents to express this kind of thing. As we've already described, the first derivative of Q, this thing I'm calling displaced charge, well, dQ by dt, that's what current is. Okay? And so we can reformulate that equation in a perfectly straightforward way and say, well, it's actually the inductance times the first derivative of current plus the resistance times the current plus 1 over the capacitance times the integral of current equals Vt. And that's each of those elements of that one should be more familiar to you if you chopped it up into 3 bits. But you can just add them all together like that. So we want to do some analysis. We want to find out how people are constructing and interpreting these equivalent circuits. And so let's start with the simplest component, which is just a resistor. So we can start with our sort of generalized series component equation. Obviously, circuits can be lots more complicated than just being in series, but it's a good place to start. We can start there and say, right, if we've just got a resistor and nothing else, and we're going to do some impedance on it, we're going to apply a sinusoidal current, or sorry, apply a sinusoidal voltage to this thing, and we're going to want to calculate the current that results. Let's do that. So firstly, we're going to set L to 0, because our system is just a resistor, so it has no inductance. And we're going to set 1 over C to 0, i.e. we can think of it, if we wish, as like an infinitely soft spring. And if you've got an infinitely soft spring, it doesn't do anything, okay? But if you set C to 0, then it's 1 over 0, which is okay, and we're going to set R to R, because there is a resistor. So our governing equation at the top just reduces down to R Q prime equals V. This is just V equals IR. Okay, I've just reduced that equation down. It's just V equals IR. We are doing this in a slightly overly laborious way because we're going to follow the same process once the circuits get more complicated. So what are we doing? Well, we know what V of t is. V of t is our applied sinusoidal stimulus. So instead of saying V of t, we're going to say that V of t is V naught, some amplitude, times sine omega t, where omega is the frequency of the applied signal. Okay? So we sub that in, and we now say R Q prime equals V naught sine omega t. Fine. We can say, what do we want? Well, we want to find the impedance of the system. The impedance of the system is current divided by voltage equals Z, right? And we're going to keep talking about that exact thing. So let's isolate Q prime. So that's our current. So Q prime equals V naught over R sine omega t. So we've now found the current that would result from the system. This is the current that comes out of that system. So if I said to you, what is the impedance? Well, it's just V over I. Okay? I know V because I chose it. So V is just V naught sine omega t. And I know Q prime because we just found it. It's V naught over R sine omega t. And you cancel all the things and you're just left with an R. I'm obviously doing this in a ridiculously over-engineered way. I'm cracking a nut with a sledgehammer here. But the sledgehammer is going to be useful when the nut gets bigger. Okay? So that's the process. We've got our governing equation. We input the parameters that we have. We choose our stimulation voltage. We simplify the system. We make it explicit for the current. Current equals something. And then we do voltage divided by current. And that's what the impedance is. Let's do that now for our first, what we call reactive component. So you've got resistance, reactance, and if you've got both, maybe you've got impedance. So if we've got just a capacitor, what's the value of L? It's 0. What's the value of R? It's 0. What's the value of C? It's C. There we go. So our equation immediately reduces to this. We do the same process again, and we say that we're going to choose to apply a sinusoidally varying voltage with an amplitude of V naught. And so we now have Q equals CV naught sine omega t. I just rearranged the equation, right? So I've now got an expression for Q, the displaced charge. I can differentiate that and I get current. That's no problem. So I had Q. I've now got Q prime. I've differentiated that thing with respect to t. And if you differentiate sine omega t with respect to t, you get omega cos omega t. So that's all well and good. But we're about to make a terrible mistake. Just like last time, Z, our impedance, should be V over I. Well, we've got I because we've just found Q prime by differentiating Q. Fine. We've got V because we chose it. It's V naught sine omega t. That's on the top. And we've got Q prime. There it is. C V naught omega cos omega t. But if we try and pursue that logic, right, the V naughts cancel, sine over cos is tan, we end up with 1 over cos omega tan omega t. Is the impedance of a capacitor 1 over C omega tan omega t? No, it isn't. It doesn't even make sense to say that, because we're looking for some kind of constant that characterizes this system, and what we've ended up with is the tan function. So there's a mistake somewhere. Can anyone tell me what that mistake is? And it's on slide 3. What's the mistake? The impedance is not the voltage as a function of time divided by the current as a function of time. It's right, exactly. Okay, so we've just found V of t divided by I of t. That's not what the impedance is. Okay, oops. That's not how this works. This is not how anything works. Okay, we don't want Z equals V of t divided by I of t. We want Z equals what I'm calling V tilde divided by I tilde, or the voltage as a function of frequency divided by the current as a function of frequency. That's a different thing. That is what the impedance is. So perhaps all of you will at some point in your career, perhaps in the first year of your undergraduate, have bumped into Fourier transforms. And most people will forget them because most people will never use them again. But here they are. And the point is, you can transform from time space to frequency space. You can represent a function in terms of how it varies in time, or in terms of how it responds to different frequencies. Okay? So here's some graphical examples. If you've just got a cosine wave, then you can transform it into the Fourier space, and what you get is a single point that just says, at this frequency, I have this amplitude. And there's a bunch of other examples given here. And you don't need to know how to do this, but you need to know what the consequences of it are. If you would like to Fourier transform some function of time, x of t, you do this integral. Okay, you just take your function, multiply it by e to the minus I omega t, and you integrate it with respect to t between minus infinity and plus infinity. That's a pain. You don't have to do that, and you don't need to do that. But that's what it is. Let me tell you some of the results of doing that and why it's going to be so important. The Fourier transform of a derivative is just multiplying the transform variable by I omega. So if you have x tilde, so x tilde is the Fourier transform of x. When I say tilde, it's that little squiggle over the top. If I've got x tilde and I want to know what's the derivative of that thing, it's just I omega x tilde. I just multiplied it. And that's the amazing power of these transformations like Fourier or Laplace, that calculus becomes algebra. So instead of doing lots of calculus type stuff where you know how to do an integral, it can be a pain. If I want to differentiate this thing, I literally just multiply it by I omega, and that is what the derivative is. The Fourier transform of the second derivative, well, I just multiplied it by I omega again. I multiplied by I is minus 1. Omega times omega is omega squared. So the second derivative is just minus omega squared x tilde. Integration is, as you would expect, similarly trivial. Instead of multiplying by I omega, I divide by I omega. Okay? So the Fourier transform of the integral with respect to time is 1 over I omega x tilde. And the lovely thing to also bear in mind is that this is a linear transformation. So the Fourier transformation of a constant times x of t plus a constant times y of t is just a constant times the Fourier transform of x plus a constant times the Fourier transform of y, where those constants are the same as they were before. So you can Fourier transform this in chunks and take the coefficients out, and you still get the same answer. Okay, and that's what linear means in this context. So let's do it again. Right, we had a go, we did it in the time domain, it broke, it didn't work. We've got a new tool, it's transforming to the frequency domain. Does it work now? So we've got our capacitor, we've got our system of our governing equation, and we're just going to Fourier transform the whole thing. Okay, so using that linearity property, well, I can take all of the constants out, L, R, and 1 over C, and I can Fourier transform each of those derivatives on their own, and I'm going to Fourier transform to the right-hand side as well. You've got to Fourier transform everything. So if I do that, here's what I get. Okay, I get minus omega squared, because it's a second derivative, times L times Q tilde, plus I omega times R times Q tilde, plus inverse C times Q tilde equals V tilde. Whatever V was, I've now Fourier transformed it, it's V tilde now. So let's do the capacitor again. Set L to 0, set R to 0, set C to C. If I do that, most of the terms immediately disappear, and I get that the inverse of C times Q tilde equals V tilde. Okay, nothing mysterious so far, I've just crossed out two of the things in my equation. Once again, and this is a bit more sledgehammer with the nut stuff, once again, well, let's choose what our stimulation is going to be. So the voltage is an amplitude times a sine wave. But I'm not even going to put it in, because whatever the Fourier transform of that is, it's going to cancel out with itself later on. Okay? So our Fourier transformed displaced charge, Q, which is now Q tilde, equals CV tilde. That's just rearranging the equation on the line above. Q tilde equals CV tilde. But now we are in frequency space. You know what the derivative of Q is had you transformed it. You just multiply by I omega. So now, when we do our differentiation, before we did like differentiate sine, you get omega cos. But now it's just multiply by I omega. So this is saying the Fourier transform of our current equals I omega C V tilde. Now we construct Z, where we say Z is V tilde over I tilde, which is Q prime tilde. So we've got V tilde on top. We've just found our Q prime tilde, which is our current that's been Fourier transformed, which is I omega C V tilde. The V tildes cancel, which is why I didn't bother subbing in. I didn't bother Fourier transforming it. They were always going to cancel out. And you end up with this expression here, that the impedance of a capacitor is 1 over I omega C, which I'm guessing you have all probably seen before. That notion is captured in this sort of simplified expression for each of these components. So if you have a capacitor, something about it is that its impedance can be described as 1 over I omega C. It's a function of frequency. Remember, the resistor was not. The impedance of a resistor was just R. It's just a real number. It's the same real number all the time. The impedance of a capacitor, not only is it clearly an imaginary number because it's got an I in it, but it's also now a function of omega. The amount of impedance depends on the frequency of the sine wave that you're stimulating with. Now we're on to something. Now we're cooking. Okay. Has anyone got any questions at that moment? I know you've been very nice and engaging as we've gone along. So we're going to do the capacitor one more time, the third take on the capacitor, and we're going to try and re-familiarize it a bit. Okay, we've been using this thing Q quite a few times, displaced charge, but we all talk in terms of currents, not displaced charges. So let's use currents instead. So rather than using Q, we're going to use integral of, rather than using q, we're going to use integral of I. Rather than using q prime, we're going to use I. Rather than using q double prime, we're going to use I prime. Okay, so I is current. So I can do the same Fourier transform as I did before, and I get this. Little I omega L I tilde plus R I tilde plus 1 over I omega C times I tilde equals V tilde. Okay, that's just the same Fourier transform type analysis as we did before, but now we're framing everything in terms of currents, capital I, instead of displaced charges Q. We'll solve for a capacitor once again. L is 0, R is 0, C is C. Sub that in, it just means crossing out the first two terms. We now have 1 over I omega C times I tilde equals V tilde. And suddenly, constructing the impedance, Z, becomes incredibly straightforward. We don't even have to think about what the stimulation was at this point. We've just got an equation that's got V tilde and I tilde already in it. So clearly, you can just rearrange the penultimate equation on that slide to be the bottom equation. So I've just divided both sides by I tilde, and I get left with the correct expression for the impedance. So we are going to use this current formulation from now on as the way of describing this system. So we'll get rid of Q, which we were helping to understand how it looks a bit like a spring mass damper or a water wheel, and we're going to stick with current I. Okay. So those were two of the fundamental components just on their own, a resistor and a capacitor. We could do an inductor. You now have the tools to do that analysis, and it would be very straightforward, and you'd find out it was I omega L. What if you've got two components in series? Well, you have the equation. So let's have those parameters as non-zero. So that's the Fourier transform version of the series component equation. So if I've got a capacitor and a resistor, then, but no inductor, then L is 0, R is R, and C is C. What happens? The equation looks like this. If I want to find Z, that is V tilde over I tilde, well, I can just factorize this thing. Right? I just factorize out I tilde and then divide it through. So I've got R I tilde plus 1 over I omega C I tilde equals V. Let's just get the I tildes on their own and divide it through to the other side. And that's that. Okay? So I divided both sides by I tilde. It ends up just being this thing, R plus 1 over I omega C. And that's kind of ugly. So we don't want that. So I just did some algebra. I just did some rearrangement of fractions. So if I've got R plus 1 over I omega C, I hope you can convince yourself that you can all do this as well. That is R plus 1 over I omega C. I want to make it, let's make it into one fraction. Well, there's lots of different ways we could express this, but if we wanted to, we could make it into one fraction. Well, I would have R I omega C over I omega C plus 1 over I omega C. That's exactly what I end up with here when I put those two fractions together. And what we will often do, what we will always do really is good practice, is realize the denominator. So your fraction is the numerator on top, the denominator on the bottom, and you want to not have any imaginary numbers on the bottom. So if you want to realize the denominator here, well, you can just multiply top and bottom by I, or by minus I is probably more convenient. And if you multiply it by minus I in the bottom, then I times minus I is just 1. And then if you multiply it by minus I in the top, you get a minus I here, and this I would disappear to be a minus 1 there as well. Okay, and so you just end up with a much simplified system. You can split it into real and complex, two different fractions as well, if you want. And we're going to see why later on that's a helpful thing to do. So in our initial framing of the problem, we had Q's, displaced charges. We now have I's, capital I's, which are currents. We know that the Fourier transformation is a linear transformation so that we can chop it all up into its little bits and take the coefficients out. We can preemptively factorize all of it. So I can put them all added together, so I can have I omega L plus R plus 1 over I omega C. All of that multiplied by I tilde equals V tilde. Once I've got V tilde and I tilde, well, I just need to rearrange it so that it's just V tilde over I tilde. And that is what the impedance is. Z equals V tilde over I tilde. So this is how we got hold of, or where you would have acquired, your three familiar impedance terms. The impedance of a resistor, it's R. Of a capacitor, it's 1 over I omega C. Of an inductor, it's I omega L. Okay, that process is how you can construct these objects. And you should be delighted about that. But obviously circuits get much more complicated than this. So the next element of complexity to add is, of course, that most circuits that you'd be interested in might have some parallel components in them. And the way that you handle them is actually quite straightforward. So you need two pieces of information. One is Ohm's law, which you already have in your back pockets, and the other one is Kirchhoff's law. So currents in a loop sum to zero, or there is no accumulation of current at a node, depending on how you want to think about it. With those two pieces of information, if we look at the circuit with two resistors, R1 and R2, you know that the voltage must equal I1 times R1, i.e. the current through resistor 1 and its resistance must be the same voltage as the current through resistance 2 and its resistance. Why? Because there is a single voltage if you measure the voltage across the pair. So the voltage must end up matching up. Okay? So if one of them's got a bigger resistance, it must have a smaller current, which makes sense. The current is going to go through the easier path. So we can also describe the system as having an equivalent resistor that is equivalent to the two that we know are really there. What would the resistance of that equivalent resistor be? Well, we also know that the global current in the circuit, okay, must be the sum of the two currents that split up along those two paths. So I must equal I1 plus I2. Okay? Those pieces of information were actually home and dry already. Okay? We know that I1 equals V over R1. We know that I2 equals V over R2. We know that I, the global current, is V over REQ, this imagined resistor that is the combination of those two components. And sadly, that's behind the thing. But you end up with a description that has basically got the voltage, which is just the voltage, it's the same everywhere, and it's the equivalent voltage equals volts over R1 plus volts over R2, and you just rearrange that. So the equivalent voltage is 1 over the inverse sum. Okay, so 1 over R1 plus 1 over R2. And that's what the equivalent resistance of a resistor that represented or could model the behavior of those two resistors acting together. So the key thing is that this doesn't just apply to resistors, this applies to any reactive components. Okay, so in general, the equivalent impedance of a parallel pair is also 1 over the sum of the 1 overs. Okay, so ZEQ equals 1 over Z1 plus 1 over Z2 plus 1 over Z3 plus 1 over Z4 if you wish. Okay, so they just have this inverse sum property, parallel resistor sum. So with all of that in mind, we can now do this circuit, which is the first circuit that has interesting behavior. Okay, and this is a parallel RC circuit. And this circuit you will bump into in many electrochemistry papers, and they'll use it to imply that perhaps a sort of charge transfer process was taking place or something like that. So we've got a parallel, we've got a thing that's actually useful for us coming up. So thinking back to our convenient formulation where we did everything in terms of the current, I tilde, well, we can just do 1 over the 1 overs. It's 1 over the sum of the 1 overs. So if I've got a resistor, R, and a capacitor, C, my impedance of that thing is 1 over the 1 overs. ZEQ equals 1 over 1 over Z1 plus 1 over Z2. That means that my impedance of this system must be 1 over R plus 1 over the impedance of a capacitor, which is 1 over I omega C. Okay? And because we've now put it in this convenient current formulation, working out the impedance becomes easy. You just divide by I tilde. Okay? So there you go, done. That's the impedance Z. I've just moved the I to the other side. Now, we will almost certainly want to rearrange this thing, as I mentioned a second ago, because it can make life much more convenient. And let's just talk through this process of rearrangement. It sort of looks like a mess, but actually it's fairly straightforward. So we've got our two fractions. Well, they're luckily for us, they are, we've made the second term in the impedance also a fraction that's divided by R, which means just multiply the top and bottom by R. So we've got 1 over R plus I omega RC over R. That's fine. We can then combine the two fractions together because they're both just divided by R, so it becomes one fraction. Once it's one fraction and it's to the power of -1, we just flip it over, and so it becomes R divided by 1 plus I omega RC. And we want to realize the denominator. We don't want any little i's on the bottom line of this fraction. How do you realize a denominator with a complex number on the bottom? The trick is you have to multiply it by something called the complex conjugate. And if a plus bi is a complex number, then a minus bi is its complex conjugate. So if our fraction is currently 1 plus I omega RC, then we're going to multiply it by 1 minus I omega RC, and a fraction that has that top and bottom. So 1 minus I omega RC divided by 1 minus I omega RC. We multiply that by what we've currently got, and we get this thing here. And it's very neat that when you multiply something by its complex conjugate, you get this squared plus this squared, but throw away the I. Okay, so we get 1 plus omega RC all squared on the bottom, and the top now becomes R minus I omega R squared C. Can anyone tell me what the units of this fraction is? It's a trick question because it's very easy. Ohms. Because it's an impedance. Okay, whatever's happening, as long as you've got your algebra right, it's still a Z, and Z has the unit of ohms. Okay, so you know that there's all kinds of weird Henrys and farads and ohms going on in there, but it will just collapse back to being ohms again. Okay. So the nice thing with that fraction is the bottom line is real numbers. 1 and omega is a frequency, resistance is a real, capacitance is a real. So the bottom of this thing could be a number like 7 at a particular frequency. The top line is a complex number. It's a real bit minus an imaginary bit. Okay, and having that separation is quite nice. Okay, and when we come to analyze it, when we come to draw it, we're going to be separating it out into the real bit and the imaginary bit, and that's how we will process the information. Exactly like this. So I've now got that fraction, and I've just chopped it up into 2 bits. So obviously you have to keep the denominator. So I've got a real bit, which is R divided by this thing, and I've got an imaginary bit, which is minus I times this thing here. Okay, so I've chopped it up into real and imaginary. We're going to see why that is shortly. And now we come to the bit that you will have seen in so many papers, which is the Nyquist representation of impedance behavior. So you have a way of graphing the impedance behavior of your system. These are parametric plots in the sense that the horizontal axis and the vertical axis are both results of the thing, and you parameterize it in terms of omega. So it's not like a classical thing where you like have y versus x and you put in x and you get y. This is real and imaginary impedance contributions. You put in different omegas and you get different coordinates in that space. Okay? So you are mapping this onto the complex plane, where the horizontal axis is the real component and the vertical axis is the imaginary component. By convention, we tend to have the vertical axis flipped over itself so that negative goes up and positive goes down. Why? Because capacitances are going to give you a negative impedance response, and most of the impedance responses that we look at are capacitive behaviors, not inductive behaviors. So if we didn't flip the axis, we'd always have to draw the graph going down, which would be annoying to look at. So we just flip it over and make it negative z prime on top, double prime. And notice these primes, z prime and z double prime, those aren't derivatives. Z prime means the real component of z, and z double prime means the imaginary component of z. Okay, and that can be quite confusing as well. So I think that's a good moment to take a 10-minute break. And then once we get back from the break, we're going to have a go at drawing these things. Okay, so please get a glass of water. I need a pint of water. And we'll see you back here at 10 past. That was a full hour. Obviously, if you've got questions, you're welcome to ask, but I would recommend stretching your legs and getting a drink.
You changed it since last year.
A tiny bit. Tiny bit. What have you noticed?
Maybe it's something I've evolved from last year.
It's true. Smaller memes. Anyone got any questions or bits that you want to understand further before we go on to this drawing? I need to work out if I can draw.
Yeah, I've never figured out how to do that.
Well, that was straightforward. Okay, fine.
Oh, that's good to know. No one else does that, have they?
Yeah.
I was expecting it to be complicated, so I saw it, and then I've just been like, neglecting it. But that actually looks quite.
It's weird that it doesn't really go. Oh,
It's not as good as I know.
How does it feel to write it now?
It's about a centimetre away from where my pen actually lands. How do I? Whatever. I mean, is it a touch screen or is it just pen? And now I'm really lost. Does that button do anything? Oh. Okay. Could be dangerous. Fine. Looking forward to it. To slide 20. Yeah. Yeah? You can have it. I can send you the slides. There's no problem. Yeah. Okay. I think, and this looks like such a mess, right? That's part of the problem. Like so many terms, so much algebra to do, and I think that puts people off, which I understand.
We used to have to derive this for the exam.
Yeah. Yeah. And I mean, although my research is quite sort of theoretical and mathematical, I'm actually not very good at maths like this. Like, I really like drawing things. I like a graph. And so this next bit's the actual good bit, because that doesn't do anything for me. You know, like I collaborate with some mathematicians who can look at an equation and be like, oh, it's really telling me something. I get nothing. It's dead. Yeah.
I have to think about it quite carefully. If I'm teaching and I have to make a derivation, and if I make a mistake or something, I find it difficult to correct it on the spot.
Yeah. I'll be doing that. Yes, and how exciting that all exams are now open book, open browser.
But it will be
open browser, right? All engineering is done with your browser open, so it's weird.
But now they will be held in person, though.
Yeah, just to minimize the temptation to cheat.
Yeah.
But yeah, open book, open browser, open code editor. I think this is wonderful.
I noticed that like in one of the exams I'm teaching that they one of the exams I was marking, the students would just written really random things in it, and then they'd obviously be googling. I recognise some paper.
Then you
from a paper, not my paper or anything, but this. So they'd obviously it was not covered, something that wasn't covered in the course, so it was completely irrelevant.
But how great that you can then, you know, assess whether someone's actually going to be a good engineer. Very exciting. By whether or not they're good at Googling. We have a raised hand. Zhao Tong.
Hi, Sam. I have a very brief question. When you talked about the linear, that part, we apply a very small potential. Do we have a commonly acknowledged a value, like how small it should be?
As far as I understand, that's a fantastic question, by the way. Thank you. It depends on the type of system that you're trying to analyze.
Mm-hmm.
Like small is a relative term, and so you need to define a little v naught based on what you're looking at. Now, if you are looking at an electrochemical system, maybe I could put Ivan on the spot and say, what's your usual? How big's your stimulating voltage when you do EIS normally, roughly?
I use 5 millivolts usually.
Yeah, so yeah, in the millivolt range, right? But if you were going to do impedance of like, people do impedance of like compressed soil stacks or concrete blocks, right? And I bet they're using a much bigger stimulating voltage there. Otherwise, they won't get any signal out the other side at all.
Thank you so much.
No problem. Thank you for the great question.
I was saying they were using it for concrete blocks. What did they get out of that?
I'm guessing it's a kind of like metric of percolation. I guess something like that. Yeah, and it's a big old thing. I mean, when you think about going across like 100 microns of an electrochemical cell versus going across like 10 centimeters of damp soil or concrete. Yeah, it's really cool. And again, you'd have a different thing if you were thinking about, you know, people do the impedance of mechanical structures. So you might get an oscillator that is applying a sinusoidal load in newtons to a mechanical structure at a range of frequencies to see when the vibrational resonances of these structures occur. I think, while we're in the break, one of the nice things is that I think one of the nicest examples of resonance, and we teach resonance in my first year maths course in design engineering, is if you get on a non-electric London bus. Okay, so you get on a London bus, and as it goes from rest at a bus stop where the engine's on, certain objects inside the bus will be vibrating. Okay, and maybe it's the seats. And then as the bus accelerates and the engine goes through different, the engine starts going at different speed. It's a rotational motion, so it's an oscillation. The bus will resonate in different ways. So you are measuring the impedance spectrum of the bus, but in a very weird sort of 3D. You're measuring the vibrational eigenmodes of the bus. And so you'll notice that sometimes the seats vibrate, sometimes the handrails vibrate, and it makes different sounds as they do because it's different frequencies of stimulation, all stimulated by the engine of the bus rotating at different speeds. But different bits of it vibrate at different speeds. And that's exactly what you're doing when you're doing impedance on a battery. That at different speeds of stimulation, you can like ring characteristic vibrational modes inside your battery. So at very high frequencies, you might have the charge transfer process is oscillating, and at very low frequencies, you might find that the diffusion process is oscillating or resonating. And that's nice because it really applies all the way up to a macroscopic thing like a bus and the seats vibrating. Yeah, is there any other? I think there were some questions in the chat. Oh, it's just the recording notification. Okay. Nice. And I can see the chat and hands and stuff, so feel free to ask anything. We'll start again in 3 minutes. I'm in campus 4 days this week, which is the most I've been in since the start of the pandemic. It's exhausting.
Don't you find it more satisfying seeing people in person?
Yeah, it's fun. It's fun.
Yeah.
Yeah. But I
And
really,
tried to
yeah.
go split over 2 campuses, and I tried to cluster together my meetings in one campus, and then, so otherwise it gets annoying that you end up having online meetings with people you could meet in person, and then
Yeah.
or come rushing here, then to have meetings with people who never come.
Yes, exactly. Is Jason here? No.
How many people online?
20.
We're not getting as many as last year.
Which makes sense because they've all learned impedance theory now. They need to learn it again. Okay.
This year you still in 17,000. How many people have seen your course here, of course?
350,000.
That's amazing.
Yeah.
Yeah.
Yeah, it's pretty wild. This is a bit mysterious. Okay. It's 10 past-ish. So now we're going to take what we've learned from the sort of moderately formal analysis approach of Fourier transforming our equation, and we're going to use that intuition and the intuition given to us by spring mass dampers and water wheels and porous plugs to draw Nyquist plots. What's a Nyquist plot? It is just the real and imaginary contributions to the complex impedance of a component or an assembly of components in an equivalent circuit across a range of frequencies. So, this is when everyone in the audience, and hopefully everyone at home, has got a pen and paper in front of them. You have a Nyquist plot template there on your graph. You can draw your own square at home. What is the Nyquist plot of a resistor? Just a resistor. It's always best to start with the absolute simplest ones to make sure you understand them. You're all used to ones with lots of bumps and ticks and flicks. What is the Nyquist plot of just a resistor? And if you're stuck with that question, what is the impedance of a resistor? Well, we've already done that, and it was just R. R is just a real number, so it should be somewhere on the horizontal axis. And it's not R omega, it's just R. So this thing isn't a function of omega. So if I say, what is it at 10 kilohertz or 10 picohertz, it's still just R. It's not a function of frequency. So if I want to add it to my plot, then okay, it's like an inch. That's crazy. Okay. R. Where the pen makes a mark is about 1.5 centimeters down to the left of where I touch the screen. That is the impedance plot of it. There is nothing more to do. There is no more analysis to do. That's the Nyquist plot of it. But obviously things get more interesting than that. So, what about a capacitor? What about just a capacitor? Well, there is the expression for capacitance. ZC equals 1 over I omega C. Let's realize that fraction. Right? We don't want it like that. That's an annoying way to have it. So let's have it like this. Let's multiply top and bottom by minus I. So this would equal minus I divided by omega C. God, this pen. So this thing, that's this thing equals minus I times 1 over omega C. God, sorry about the pen. Minus I times omega C. Does my pen work? So it's minus, I'm going to try and write that. It's minus I times omega c. That's better. Okay. Now, this is clearly an imaginary number. It's always times minus I. Don't forget, with the Nyquist plot, the vertical axis, the imaginary component has been flipped, so negative is up, positive is down. If omega is some number, like 7, the frequency is 7 hertz, then our impedance is going to be minus I times 1 over 7 times whatever c is. C could be 3, so it would be 1 over 21. That's minus I times 1 over 21. That's just somewhere on that vertical axis. It's just a position somewhere on here. A position somewhere on here. What we're going to do in each case is do some very crude limits analysis of limits. So we're going to say, what is the limit as omega goes to 0 of zc? I put crosses through my z's. Well, as omega goes to 0, that 1 over omega is going to explode off to infinity. Right, so I'm going to use slightly sloppy notation here, forgive me, but I think it makes life easier. So this thing equals minus I infinity. And we're going to do a limit as omega goes to infinity, so at very high frequency of zc. What happens there? What happens as omega becomes a very large number? 1 over omega becomes a very small number. So this is going to go to 0. Okay? So we can add a bunch of... impossible. A bunch of points, because every value of omega is still just going to be another point in that vertical axis. There's no value of omega that would give a real contribution to this thing. And so as we go down here to 0, then omega is going to infinity, and omega is going to 0 up here. So that is the Nyquist plot of just a capacitor. It's a vertical line on the vertical axis, but it's constructed of points, and as omega goes to a very large number, it comes close to the origin. As omega goes to a very small number, it shoots off to negative infinity. Okay. And your next screen touch will be a right click. Right. Nice. Okay. Let's do it again for an inductor. We haven't seen the inductor in a while. We introduced it at the start, and we're now going back to it. Can you do this analysis? It's slightly easier, actually. Okay? Do that crude limits analysis. What happens when omega becomes a very big number? What happens when omega becomes a very small number? Ugh. So once again, every point is going to be on the imaginary axis. There is no real component, but it's now positive in the positive I direction. So it's actually going down off this graph. Down here.
Sorry to interrupt you. I think for some reason it is not really updating this. Can you just try to stop sharing and share again?
Yeah.
Was it maybe something to do with just how it appears on the display? Or was it appearing before?
Was it Oh, like, I
If I go,
was looking at this.
if I go, what about now?
It's just the back.
Well,
It's
that's
weird that it goes.
bananas.
So just save it on. It's not just a display, right? Just save it, but if you go backwards, it.
Yeah. Yeah, that's a good point. That is so weird. Well, for those online, you don't get the secret hints and tips. Hopefully I'm describing it vividly enough, but it is all available on the YouTube video.
You should be able to see on the camera.
Yeah. Yeah.
Not so well though. But
Okay, if you've got any questions, I mean, I am looking at the chat. So if you, the pen does not appear. Slides move fine. Thanks, Angus. Do this limits analysis. Okay, I will describe it in vivid terms. Okay, for the inductor, as omega goes to 0, clearly I times 0L is 0. And as omega goes to infinity, I times infinity L is going to be a very big number. It's going to be I infinity. Okay. So that's now just a vertical line, but going down. Okay. Let's do a combination of elements. So a resistor and a capacitor. Sorry, online, you just won't see this. Unless I... no, too complicated. Too complicated. Okay. So.
what happens if you try sharing again?
Okay, yeah. I've got an idea. I'm not going to share the window. I'm going to share the screen.
Yeah, that usually.
Yes.
Yeah?
Yes.
Nice. Ridiculous, but I'm glad it's come out. Okay, that's a resistor. That's an ugly capacitor. That's an awful inductor. Here we've got RC in series. Okay. So RC in series, well, we did all the we've done this one already. We did the analysis of it. We've come up with this result. I recommend to you to both realize the denominator and split it into two parts, a real part and an imaginary part. And that's what we have over here, this thing. So we want to test this at a range of frequencies, just like before. So we can do a limits analysis, and we can say the limit as omega goes to, let's say, very large first of z equals, well, as omega becomes very large, this is a 1 over omega, so that term's going to go to 0, so it just becomes r. So we've got a point here, and it's just the point r. Okay, what happens in the limit as omega goes to 0 of z? We have got, well, as omega goes to 0, this thing's going to explode off to infinity. So it's going to become r minus I infinity. People squeamish at home because this is not a very formal way to do limits. I don't care. This is useful for drawing diagrams. Okay, so what does that mean? Well, the real component stays constant. So it's just always in the same place on the real axis. But the imaginary bit is going from 0, exploding up to negative infinity. So we've got, oops, this thing's going off up here like that. And we've got omega going to infinity here and omega going to 0 up here. Okay, so it's just that vertical line again, but now it's been shifted horizontally by a factor of r, or by r. And this is kind of what it's all been building towards. This is the first interesting one, right? The others are not very interesting. What does a parallel RC circuit look like? And I would love you all to really have a go, right? Have a go at constructing this yourself. I've done the algebra for you. If you look at the screen, it says, as we've already constructed in our previous slides, the impedance of this thing can be split into a real bit and an imaginary bit. And the real bit is r over 1 plus omega rc squared. And the imaginary bit is minus I times omega r squared c over the same denominator, 1 plus omega r c all squared. So test some values of omega. Let's do the same limits analysis that we did before. So the limit as omega goes to what do we want to do first? Infinity is more fun. Infinity of z equals, well, let's look at the real bits. So it's r over 1 plus omega rc squared. So as omega goes to infinity, the denominator is now a huge number. So it's going to be r divided by a huge number. So it's going to be 0. Minus I times, so we've got like an infinity divided by, very hand wavy here, but it's an infinity divided by an infinity squared. Right? As omega becomes very large, this fraction becomes omega r squared c divided by omega rc squared. So you end up with an omega divided by an omega squared, so it's just a 1 over omega. As omega becomes very large, a 1 over omega becomes very small, so it's also 0. This thing is just 0. Okay. What about the other limit? Limit as omega goes to 0 of z equals. So what's going on here? So it goes to 0. It goes to 0. So we've got our r divided by 1 plus 0 squared. Right? So it's just r divided by 1. It's just r minus I times, no, minus r times, and set all the omegas to 0. So it's 0 on the top, so it's going to be 0, isn't it? So 0 divided by 1. So it's just 0, so this thing equals r. Okay? So we've got 2 points. These are impossible to draw. There, one of them is there, and one of them is here. R and 0. Okay, so we've got 2 points, but you all know that this thing is more interesting shape than the others. So how do we find that shape? There is now a third point. You're engineers, you can brute force this. You can just chuck lots of values of omega in, and it will plot the right graph. But there is there is a better way. Okay. And that's what the impedance spectroscopy machine is doing, right? Let's do all of the values of omega and see what comes out. It doesn't know there's a semicircle. It knows there's points. Okay, you are saying there's a semicircle. There is a nice value of omega that we can pick that simplifies the equations. Okay, look at those equations, and think about a value of omega. Frame it any way you want that would make lots of bits of the equations evaporate into dust. Does anyone? Can anyone think about it? What value could omega have that would cause bits of the equation to disappear? Right? Well, look, what is omega multiplied by often? It's multiplied by RC. So if omega was 1 over RC, then 1 over RC times RC is 1. Okay? So at omega equals 1 over RC, sum in. What do we get? Z equals, well, it's R divided by 1 plus omega times RC is now just 1. So 1 plus 1 squared, which is 1 plus 1. So R divided by 2. R divided by 2. And what about the imaginary bits? We'll have minus I times omega is 1 over RC. So we've got 1 over RC times R squared C. So that's just R on the top. R. And same as we got last time, it's just going to be 2, isn't it? Again, 1 plus 1 over RC times RC squared. 1 plus 1 is 2. 2. Okay. So there is an interesting thing that's just happened. Our impedance at this particular frequency, RC, or sorry, 1 over RC, is R over 2 minus I R over 2. So it is here-ish. This is R over 2. Okay, so we've got something cool has happened. Now we've got a point that's got some imaginary contribution to it. Now, this happens to be a parametric equation for a circle. And we're not going to explore negative frequencies, negative values of omega, because they don't mean anything to us. But in the positive, it ends up being half of a circle. It's a semicircle. You could find this for yourself by subbing in other values of omega. We could have omega equals 2 over RC, or omega equals a half over RC, and you will recover points here and here. And you could have a quarter, and you could have 4 times. And what you'll find in the end is that it looks like that. And it will become a semicircle. And this over here is as omega goes towards R, as omega goes towards 0. Can anyone tell me what the units of R times C must be? I think keeping a handle on units is such a good skill, such a useful thing. The units of R times C. Well, the units of 1 over R times C must be the same as the units of omega. And omega is a frequency. So it has the units of inverse seconds. So RC must have the units of seconds. So RC is a characteristic time, tau. Okay? So this thing here is tau c, the characteristic time, equals RC. That's when it occurs. And we could also add the annotation to say this is R over 2 as well. Okay, so we've got a semicircle. The peak of that semicircle is at the characteristic time, and that goes back to the wobbling bus, where at a particular frequency, you will find the sort of resonance, the point where it's most out of phase. And that's what you're looking at here. And so you've got a process, and it's got a characteristic timescale. You have to probe that frequency in order to see that process, otherwise you won't see it. Okay. Yeah. So a request for you all when you write your beautiful papers is please always include frequency information on your Nyquist plots. If we go back to this plot here and imagine that I've just plotted a semicircle, I might say, oh, that might be an RC parallel thing, but I don't have any real insight into what kind of process it could be, because I don't know where the peak is in terms of frequency, so I don't know if it's a very slow thing or a very fast thing. So all Nyquist plots, if you're going to publish them or talk about them, should have some key points on them annotated with the frequency at which they were measured. It's nice to actually use points that are intermittently changed, so like cross, circle, that have decades of frequency built into them. So, you know, kilohertz, 10 kilohertz, 100 kilohertz, whatever, so that your reader can really get a sense of the frequencies that they are looking at. The frequency is how you see the capacity. Okay? Otherwise, you've got no idea really what's going on. So if you show this, and so in order to teach myself impedance theory, so I'm a mechanical engineer and I joined a materials science group to do my PhD and knew nothing about this or about materials science, and would just go to meetings and just come away having learned nothing. Go to group meetings and just be bamboozled by everything everyone said, because I didn't have any of the language, any of the vocabulary. And so that is, I guess, what starting a PhD is like for a lot of people. And so you just go away and start incrementally trying to piece some of this stuff together. What's a perovskite? What's a charge transfer reaction? What's a Nyquist plot? And so I was particularly fascinated by impedance, which is why I'm here now. And so I built for myself, it's like a little piece of code that makes plots for the equivalent circuit that you can see there. R, RC, RC. Okay, in the top of that graph. So it's a resistor in series with a parallel resistor capacitor in series with another parallel resistor capacitor. And all of their values of each of the components are written there. So half an ohm, 2 ohms, 1 ohm, 1 farad, and 0.0005 farads. Okay? That is the Nyquist plot of that system. Okay? And I now I can look at that and find it very natural. For example, there's a resistor. Well, if there's going to be a series resistor anywhere in your circuit, it's just in series with everything else, it's just going to shift everything along by the size of that resistor. So here's 1, that resistor is 0.5, so it's not surprising that the first thing here is 0.5. Okay, just going to shift it all along. You then have 2 parallel RCs, and you end up with 2 semicircles. But I suspect that many of you will know that that's not always the case. And this is the sort of, well, the one of the nicest bits that I hope you can come away from today if you had not previously understood this. I've labeled everything, right? Here's omega going off to infinity, down here. Here's omega going off to 0, down here. Slow processes to the right, fast processes to the left. I've also labeled the 2 taus, the 2 characteristic time constants. They are the peaks of my 2 semicircles. Tau of 0.005, well, that's just RC. 1 times 0.0005, that's tau 2. And 2 times 1 is 2, that's tau 1. Notice, the blue semicircle is on the left and the red semicircle is on the right. But the red pair is on the left and the blue pair is on the right. The order in which things appear in a circuit in series has absolutely no effect at all on how that circuit depends. I.e., if I put that half ohm resistor all the way over to the right or in between the two, it doesn't change anything. Right? You experience everything all at once in an equivalent circuit. So the ordering doesn't matter. Clearly, the ordering of whether things are parallel or series, that matters. But the order in which they are presented in series is irrelevant. So it's got 2 semicircles. And what's happening is, and I think it's nice to go back to the mechanical or the water wheel structure, but basically, if you imagine you're a water wheel, you're not a water wheel, you're a water circuit, you're water. And you could go through 2 different paths. And one of the paths is like a sort of porous constriction. It's quite hard to get through, makes you turbulent. And the other path has got a elastic membrane in it, okay? Which is like the spring in the spring mass damper, or like the capacitor. And the porous plug is like the resistor, or like the damper, okay? You can go down one of those 2 paths, okay? If my capacitor, my spring, is very soft, then it's easy to go down this path. Okay, and if my porous plug is very sort of narrow and got sort of windy path, then it's very hard to go down this path. But what you have seen is that's a sort of time domain analysis. How easy is it to go down? But we're thinking about frequency, and what we have observed is resistors don't change as a function of frequency. So it's always equally difficult to go through a resistive porous plug or move a damper around or through a resistor. Frequency doesn't change anything. But the capacitor, the ease with which you can pass through and back through a capacitor does depend on frequency. Okay, 1 over I omega c. So as the water, or the electrons, as the water is choosing which path to go down, it's going to depend on the frequency with which, because it's not going down, it's going backwards and forwards. It's going to depend on the frequency at which you're trying to do that thing. Capacitors are these membranes that are filling up with displaced charge. Okay? Well, that's one way to think about a capacitor. Or a spring that's getting stretched out. And it's proportional to the amount that's in there. And so as you do things very slowly, i.e. a low frequency, the capacitor is going to get full. The spring is going to get very extended and start pushing back really hard. And so you're just going to go through the porous plug instead. So high frequency, if you want to go forward and then back and then forward and then back, this elastic membrane Well, it doesn't care. You're deforming it so little before you start going back in the other direction again. It's as if it wasn't there at all. So with a capacitor, and as you'll notice from the Nyquist plot, as frequency goes to infinity, the impedance goes to 0. So if you want to push things backwards and forwards through a capacitor, it's as if it's not there. It may as well just be a wire. If you try and do it more slowly, the capacitance shoots off to negative infinity, reactance shoots off to negative infinity, and that's because you're moving it through and it gets full and is pushing back really hard, and you come back this way, it gets full this way, and it's pushing back really hard. So capacitors turn into wires, or can be thought of as just a wire at a high enough frequency, and can be thought of as an open circuit at a low enough frequency. They become fully blocked. So at a low enough frequency, both of these capacitors, irrespective of their value of C, at a low enough frequency, a super ultra low frequency, they're just both full. They're really extended springs that are pushing back really hard, which means this circuit becomes a resistor, followed by a resistor, followed by a resistor. And so the impedance of the system becomes R1 plus R2 plus R3. Because there's no way through those capacitors, because they're so stretched out springs, they're so full. Okay? And that's exactly what you see. As omega goes to 0, it becomes a half plus 2 plus 1 is 3.5. Okay? So we've got this point, it's just a half. We've got this point, it's 3.5. We know where semicircles come from. And the key thing is to notice those two values of tau, the two time constants, are very different. I'm going to show you an animation now, and we're going to then try and understand what's going on. And I think we'll just let it run. When this thing animates, what you are going to see is I am going to change one number and one number only. C2, the capacitance of the blue capacitor. And I'm going to start doubling it. Doubling it, doubling it, doubling it, doubling it. Okay? And as I do that, I'm also going to plot at the same time what the impedance spectrum will look like resulting from that thing with that particular value of C2. The result are the green crosses. Now, currently the green crosses sit exactly behind the blue and red circles. But they will not do that all the time. Okay? I also am constantly updating everything that you can see. So the two values of the time constants will change. In fact, the red time constant will stay the same because it's always going to be 1 ohm times 1 farad, 2. But the blue time constant is going to start doubling as well. Okay? And you'll notice R2 is just 1, so T2, tau 2 will often just be the same as C2, same value. They've swapped sides. C2 is now massive. Okay, it's coming back down again. So I'm halving it now. Half, 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 half. Okay, and you can see that I've got some labels on the green. The green is the resulting Nyquist plot, but it is the resulting impedance spectrum, but it's also spaced in steps of root 2. So every 2 crosses along gets you a factor of 2 increase in frequency. And I've got one particular point labeled with a green circle, which is 1 hertz. So you see the green circle? There it is. It's 1 hertz. The green circle and the red circle are always 2 steps away from each other, because the red circle has a time constant of 2, so it's half a hertz. Okay? The green circle is 1 hertz, so it's got a time constant of 1. And the spacing between crosses is root 2. So times root 2 by itself, you get 2. So the green and the red stay. But watch the blue circle. It's traveling along the thing in steps of 2 crosses at a time. And eventually it sort of gets too small to be able to do that. But once it gets picked up by its appropriate cross, then it'll start hopping. Hop, 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 hop. Okay? The time constant of the process being represented by the blue RC pair is changing. There is a moment Now, where the time constants of the two processes are the same, tau1 equals tau2. So R1 is 2, C1 is 1, R2 is 1. So when C2 is 2, that's when the two time constants are the same. And when the two time constants are the same, you get one big semicircle. It is impossible to distinguish whether one big semicircle is one process, two processes, or an infinite number of processes if they have the same time constant. And that's one of the big challenges with impedance spectroscopy. If your multiple processes have similar time constants, then everything gets jumbled up into a big blob. And that's when you start to think about sort of Arrhenius laws, where you start thinking, okay, well, maybe I need to do this experiment again, but at a different temperature, or a different pressure, or a different concentration, such that I can shift the time constants of my processes away from each other and uncover a spectrum where the processes are nicely separated. The maths of this is no more conceptually difficult than what we've just done. You just add on another 1 over the sum of the 1 overs for the next RC pair. It's just more algebra. But you can, there's nothing more to do. It's R0 plus 1 over the sum of the 1 overs R1 and C1 plus 1 over the sum of the 1 overs R2 and C2 kind of thing. You add it all up, you make it into one big fraction, you realize the denominator, you separate it into real and imaginary, and you do that analysis with omega, and you plug a bunch of different omegas in, and you would get the green line. It's a pain because it's lots of algebra, and you would let the computer do it instead. But you notice that that green curve, the real recovered, the impedance spectrum that you get from the circuit, has this really interesting thing of going from being two semicircles when the time constants of the two processes are really separate to merging together. And I like to think of like a puff of air coming up from underneath the graph and sort of blowing like a sheet, so the green sort of gets blown up until it becomes one big semicircle, and then they swap sides and go down the other side. So the slow process is always going to be on the right, so the one with the longer time constant. Okay. And obviously, once I've written the code for that, I may as well do it for lots of other stuff. So there are a range of other elements that you will have bumped into. One of them is a CPE, a constant phase element. They get a lot of like weird side eye from people saying, oh, that's a non-physical thing. They're all non-physical things. There is no resistor that is truly not a function of frequency. There is no capacitor that isn't, all of this stuff is idealizations, okay? The CPE, this constant phase element, as the name suggests, is a component with a constant phase angle. A capacitor has a constant phase angle. It's just vertical, and it just goes up the vertical axis. The CPE has one, and it's non-vertical, so it's going off in some direction. This tells you in this version of it, where I put two different CPEs in, that it's the slope, it's the initial slope of where this thing is. And you could draw this down, and there would be a full circle with the center not on the real axis, whereas the centers of the semicircles of an RC pair have the center on the real axis. These ones are depressed. And so this one's got that slope, this one's got that slope. And there's all kinds of complicated bits in here. And I'd be happy to do maybe at some point like a session on more elaborate components. But just watch it. It won't probably do what you expect it to do. So I'm just going to change the capacitance of the blue one, Q2. What do you think is going to happen? Make a prediction in your head as I scroll through different values of Q2. Ooh, that's very exciting. Here we go. It's gone inside the red circle. All those time constants are still there. You can. CPEs have got two parameters, this Q and an alpha, and the alpha tells you the sort of angle of the line. 0 is flat, 1 is vertical. Look at that, it's very weird. So you can draw your sort of depressed semicircles underneath it, but actually the lines don't even, the green doesn't even sit on top of them necessarily. You see it looks just going to intrude inside the red one. So it can be quite a lot to try and by eye deconvolute all of these processes. This is the analytical expression for the CPE. 1 over some parameter Q times I omega to the power of alpha And when alpha equals 0, it's just a resistor. Right? If you set alpha to 0, then anything to the power of 0 is just 1. So 1 over Q naught, well, Q naught just becomes 1 over R. Okay? And when alpha equals 1, it's just a capacitor. It becomes 1 over a number times I omega. So that's what a capacitor's equation is. So when it's something in between, you get something in between. And it's just this diagonal line. And that really, I'm now just going to, in the next sort of 5 minutes or so, just going to speedily go through a bunch of other small topics. Nyquist plots aren't the only way to represent this kind of information. You can also have a distribution of relaxation times graph, or you could have something gamma, which we don't have time to talk about today, and tau, your time constant, for each time or frequency, you'll find these sort of processes that can look something like this. And this, in some cases, can feel like an easier way to visually deconvolute the processes that you see. However, it's never as simple as you might expect, and you have to add more data in order to make this transformation coherent, and you end up doing various kinds of regularization to fit nice curves to the data so you can have a greater degree of discretization, and that causes no end of problems. So if you see a beautiful DRT plot, your first thought should be suspicion, because a lot of processing had to be done to turn your impedance data into that DRT plot. They are wonderful when you have them, but the data had to be treated quite significantly to create it. So that's something to bear in mind. So you might say that this is a slow process, so this could be diffusion here, and this could be charge transfer down here, and that looks terribly appealing, but it is often hiding a lot of complexity. There are elements that model diffusion, okay? And they can be like a Warburg element. Sometimes you might write it like this. And we have analytical solutions to the diffusion equation in systems where you can flow in and out the other side, but you've got to diffuse through it, or in one side and it's blocked at one end, which is a very common system in electrochemistry. And you can think about these as an infinite series of resistors and capacitors connected to a common rail. And I'm very interested in this topic. I've written a solver for this in 3 dimensions. And so if you want to talk about Warburgs, I'd be delighted. Gerischer elements where you've got reaction and diffusion happening at the same time. Again, very common in electrodes. Not only is your stuff diffusing through the electrode, but also as it's touching the porous electrode, it might be disappearing a little bit as it's going along. And you end up with a adorable hedgehog like this, a little smiley face. And that is another shape that you might observe in your stuff. All of these are still idealizations. Okay? So never think, oh, it doesn't look quite like that. It's definitely not going to look right, because your electrode is very likely to be 3-dimensional and have all kinds of varying properties as a function of space. It might be more porous near the top and less porous near the bottom. So it will end up being an interesting distortion of this and have all kinds of wobbles. But it might still be Gerischer physics that's governing it. There is equivalence to bear in mind. A resistor is just a parallel RC pair where C has gone to 0. So you've got a parallel RC pair. You can go down one of 2 streams. But if your capacitor doesn't let anything in, then it just is a blocked bit. It's just an open circuit. So this is what's crazy about this. If I have a parallel RC pair, it looks like this. But if I make C very, very small, then that's going to change where this time constant bit happens at the top. Okay? If I make C 0, then it's impossible to ever escape this point over here, and so you just always end up as R. Okay, it's a slightly abstract point, but if this thing is a parallel RC pair and C is 0, it is just the same as it being a resistor. Another one that's, I think, probably more nice is that a capacitor is just a parallel RC pair as C goes to infinity. That one seems a bit weird, but if I've got a semicircle, well, as R goes to infinity, this semicircle is getting very large indeed. Okay? And you imagine, as R goes to infinity, it's just become a vertical line, as far as you can tell. As far as any frequency that you can possibly measure, it's just a vertical line, because it's just a semicircle with an infinitely large radius. And that's part of the notion of equivalence in these equivalent circuits. There are many different representations that you can use to represent the same behavior that you actually are able to observe. Very, very briefly, here's some of my own research where I like to simulate and image things in 3D and run some of the simulations in them. And here's like just diffusion behavior, but it's doing some very weird things in the Nyquist plot. And so don't be surprised if your impedance data doesn't look exactly like the idealized elements. Here's a set of different elements that you could diffuse through and all the different impedance that you might observe. The black dense line is the analytical solution. It's a Warburg, it's a finite length Warburg element. All the colored lines are what happens if you actually try and model that in a weird microstructure. And also different definitions of things like tortuosity factor. This is the electrode tortuosity factor. Oh no, this one's actually just what happens if you've got a graded porosity. Particles, porosity changing as a function of depth, very common in electrodes, and you see very distinct behavior. And also inset is a nice distribution of relaxation times graph. This is a different definition of tortuosity factor, and it allows you to see when electrodes are changing their porosity, graded electrodes, and this changes how, for example, a battery or a fuel cell might perform. You don't want all the pores to be blocked at the top. That would be very bad. But you don't care if all the pores are blocked at the bottom next to the current collector. It doesn't make any difference. There's nowhere to go anyway. Nice little bit. The conductivity of pure copper is, 60 times 10 to the 6 Siemens per meter. But copper with a tiny amount of aluminium has been reduced by a very significant amount, 30% reduction. So when you're thinking about trying to analyze elements, don't forget that you almost never get to interact with elements, right? Everything is a mix. Symmetrical cells, people often build symmetrical cells to reduce complexity, but don't forget, if you've got a symmetrical cell with what's usually your cathode material facing what's usually your cathode material, at any particular moment, one of them must be acting as an anode. And that's a really important thing to bear in mind. Just because they're both made of the same thing doesn't mean they're both being cathodic, right? One of them is doing the thing it doesn't usually do. And you need to take that into account. And if one of them is likely to dominate the processes that you see, I have the greater impedance. So you might end up measuring a thing that you're not interested in at all, which is how good is my cathode at being an anode, for example. And with that, we have 5 minutes to. Thank you so much. I know it's a bit of a marathon, and thank you all for answering my questions when I've picked on you and pointed you out. And I'd be happy to take any questions. So thanks again. Whew. That's impedance. So there you go. Please go ahead. In the chat, you're welcome to just ask your question out loud. Who is it? Oh, it's same as before. I think Jaton is it. Yeah. Oh, hello.
Hello.
Hi.
Thank you for your presentation. I have about taking the EX data. What do you usually use to fit the Nyquist plot?
I actually don't. But people use ZView a lot. What do you guys use? ZView? What's the go-to software? ZView or ZFit? Yeah, I see those people in the materials department use those quite a lot. Yeah. But
Also, the potential stats has
some proprietary software that comes with it. Yeah. I don't, because I don't measure real impedances. I simulate them, so I don't so I don't know what they are. Yeah. And there's endless additional complexity that we could go into on another day if people wanted to. But all these things like having your data not violate Kramers-Kronig relations and all these important things that you need to check. But 2 hours is enough.
I tried that plot, but the result, the fitting doesn't look very nice to me. So that's why I asked this question. But thank you anyway.
No problem.
And
Go ahead.
And I have a final question about the bold plot. So, like, I think Nyquist plot is quite popular because it give information very straightforward. But I also see people sometimes use bold plot, and I do believe it can deliver some different information compared with Nyquist plot. Could you shed a little bit light on that?
Yeah, that's a really good point. And actually, I should have put some Bode plots in here. Bode plots would just be just the real part against frequency and then just the imaginary part against frequency. And they are actually probably in general better. And I know that's a very arm-wavy statement, but they're a really clearer often way of representing the information that you have. And I think actually in general, it's nice to have all three. And so as a figure, rather than just having a Nyquist plot, to actually have a Nyquist plot and next to it to have a composite Bode plot that's got two different vertical axes, one real, one imaginary, and your frequencies coming off it. That's a really nice way to look at the data and gives people a really rounded sense of what's going on. People often just put the Nyquist plot, but I actually think that's a really good point. And in general, it's nice to have both, at least in the supplementary, if not in the main paper. Because generally, you really can't tell what's going on in a Nyquist plot. Like, either it's right or you're lost. I think fitting the data is often very difficult. One of the things to mention as a last thought is that from a measurement perspective, unless you're very careful, you will also be measuring the machine that you're trying to do the measurements with. And so the wires that connect it to your sample will have their own impedance, and they will often have inductance properties as well. And if you've got very long wires because you're trying to put it into a big thermal chamber and keep your potentiostat at the room temperature, then you're just going to measure your wires. And there are ways of getting around this which involve normalization. So you start the thing by measuring an open circuit and then measuring a highly conductive thing. And then you can use that information to move your measurement plane right up to your sample. But even then, you've got to attach your thing to your sample, so you get terrible contact resistances and all sorts of mess. So the process is never as clean as I get to explain it in a theory lecture. And I think Jason is the one who's explaining what it's actually like to do impedance, which I've been reliably informed is an absolute nightmare. But the theory is charming, so that's why I teach this bit.
Sam, what confuses me most in Bode plot is it have two y-axis. One of them is the phase shift, right? The other one, the log of impedance is quite straightforward. But when it comes to phase shift, how do we understand that?
Good point. So there are 4 different Bode plots you could have. All of them have frequency or maybe log frequency as their horizontal axis. You can have 4 different vertical axes: real, imaginary, magnitude, and phase angle. And for each point, for each green cross, let's have a green cross here. For this particular frequency here, there is the magnitude, which is the length of the line connecting that. And there's also the angle, which is that angle down there. Okay, and so for every different point, and therefore for every different frequency, you can report the real, the imaginary, the magnitude, and the phase angle that is required for a polar coordinate, for a vector to get to that point. And so when you're talking about phase angle, you can see that when things are getting very out of phase, that's when you will have perhaps stimulating a resonance of your system, i.e. that's when you're most likely to be looking at a particular process, and your phase angle might reach a local maximum in that region. Does that make sense? It's a very quick description, but hopefully that's helpful.